Okay, so today we're going to start Chapter 8, Complex Numbers, Polar Equations, and Parametric Equations. And we are really only doing part of this chapter, but we will visit more of it next semester. So jumping right in, complex numbers is something that you saw in Algebra 1. Complex number, you know, your friend I. So I comes from the fact that there is no real solution to the statement x squared equals -1, and that's because x squared literally means x times x. And if we want x squared to be a -1, the problem lies in this fact. If x were positive, a positive times a positive is always going to result in a positive. And they both have to have the same kind of sign because it's the same thing. X squared means something times exactly itself. If x were a negative times a negative is also a positive. So there's no way to have something squared and have it result in a negative because positive times positive is a positive. Negative times another negative is a positive. I can't result in a negative. So by definition, I is the square root of -1. And we use this a lot. I squared is equal to -1. And if you don't believe me in that one, if we all agree that I equals the square root of -1, then I squared means square root of -1 times the square root of -1, which results in -1. So our imaginary numbers combine with our real number system to make what we call complex numbers. So you have A and B, and they are real numbers, which means they're part of the number system that you are used to. And when we put them in the form A plus BI, it becomes what we call complex, because A is the real part and BI is the imaginary part. Complex numbers have some important properties. So important properties, let's see. If two imaginary numbers are equal, they're equal only because A equals C and B equals D. So what that means is that their pieces have to be the same. The real has to equal the real, and the imaginary has to equal the imaginary. When we take a real piece, RA, and we add it to our imaginary, BI, then the whole thing becomes together a complex part because it has a real and an imaginary piece. So keeping in that theme, if B equals 0, then A plus BI is just A, which means it's just a real number, something we have always been used to. If B does not equal 0, then A plus BI is what we call a complex number, what I said right here. If A equals 0 and B does not equal 0, meaning you only have a B part, then this is what we call a pure imaginary number, like here and here, because it has no real part. It's not complex. It's solely imaginary. The bottom statement, I don't know why they don't bold the whole thing. It's very important, and your homework's a little bit sensitive when you type it in the computer. A plus BI is called standard form. So please make sure you write them in that order. A plus BI, or you can write A plus IB, but the real comes first and then the imaginary. Furthermore, when we have expressions, we usually write the I in front of the root instead of like this. This is a big no-no right here, because then we think that the I is actually under the root, so it's a double square root. So put the I in front of the root, not behind the root. This is something I'm sure you haven't looked at in a long time, but you looked at this in, I think, Algebra 1, definitely Algebra 2. It categorizes all the numbers that you use in life. So we have our real numbers and we have our non-real numbers, and together they make up the complex number system. So this peachy color and this blue make the complex numbers. And then inside the non-reals, we have pure imaginaries, the things that don't have a real piece at all. And then inside the reals, we have lots of things that you're used to: natural numbers, whole numbers, integers, rationals, and irrationals. So we're going to use what we know about I to simplify some stuff. So before we do that, as long as a is greater than 0, then when you have the square root of a negative number, you pop that negative, that I out. What you're really doing is the following. For example, let's say I had the square root of negative 7. You can break this up into negative 1 and 7. So you have the square root of negative 1 times the square root of 7. And the square root of negative 1 we call I, and then root 7, which is exactly what happened right here. So we're going to use this property, and we are going to rewrite and clean up the things that we have below. So the first thing I'm going to do always is deal with that I. So this is going to be I root 16. Square root of 16 is 4, so this is just a 4i. Next one, I'm going to deal with the I and then the root 70. 70's factors, 1 and 70, 2 and 35, 3 doesn't go into it, 4 does not go into it evenly, 5 goes into it evenly, 24 times. That's not right, sorry. 14 times, not 24. 6, 7, and 10. And then we're just going to loop back around the other way. So if you look over here, 35 is 7 times 5. Neither one of those are prime or have things that go into me that are rootable or have a square root, so I'm going to leave it. 14 is 7 and 2. Again, nothing that's going to help me. 10 is 5 and 2. Nothing that's going to help me, so I'm going to leave it as I root 70. The next one, I'm going to do I and the square root of 48, deal with the negative first always, and then we're going to rewrite the 48. So I'm going to keep the I, and 48 I can rewrite as the square root of 16 times the square root of 3. If you didn't pick 16 and 3, we could have done 8 and 6. Lots of different ways to do it, but I always try to find that square number, that perfect square. Square root of 16 is 4. Remember, we write the I in front of the root, so 4i root 3. Just in case you don't remember how to do this, I'm going to do it. You may not have all known that 16 went into 48, so write it like this. Name all the things that can go into 48. So I did it over here. If I kind of prime factorization, 48. 48 is, I hope you all could do 8 and 6. 8 is 4 times 2. 6 is 2 times 3. And this is 2 times 2 times 2 times 2 times 3. So in here I have 2 times 2 times 2 times 2 times 3. It's the square root, so I have to make pairs. So one blue pair gets to pop out, so 1, 2 pops out. Another pair gets to pop out, so I get another 2. So on the outside I now have a 2 times a 2, which is where my 4 came from. 4 i's, and then inside that root 3 cannot come out. So now that we know we can simplify statements with I in them, let's use this property to solve. So if I want to solve number 2, I'm going to square root both sides. The previous problem, there was already roots on the paper. So because there was already roots and no plus and minus there, we could do just the positive or the principal root. But now I am creating a root. And so when you create a root that was not on the paper to begin with, you also have to put the plus and minus when you're doing square roots. So I'm going to square root both sides. X squared equals plus or minus the square root of negative 9. X squared equals plus or minus, I'm going to have the I come out, but the square root of 9 is 3, so 3i. Your book writes them as a solution set like this, plus or minus 3i. Next one, I'm going to subtract the 24 over to both sides. X squared equals negative 24. I'm going to square root and say that x equals plus or minus the square root of negative 24. 24 is 4 times 6, and the square root of 4 is 2. So x equals plus or minus 2i root 6. Again, your book writes things as solution sets. Plus or minus 2i root 6, like that. Okay, so in the box below, the caution box, it is telling you and warning you exactly what I've been saying, is that if you have the square root of a negative number, we're going to deal with the I first before we do any radical or root properties. So let's use that idea and that concept to simplify the below. So in letter A, I have to deal with the negative first. So I get I root 7 times I root 7. I can multiply in any order that I want. So I times I is called I squared, and root 7 times root 7 is just a 7. I squared is a negative 1 times a 7, so the answer is just negative 7. On letter B, the I pops out, square root of 6, times I pops out, square root of 10. I get I squared, square root of 60. 60 is 15 times 4, so I have I squared, square root of 4, square root of 15. Square root of 4 is 2, so I get, this is 2I root 15. Oops, sorry, 2I squared. I squared is negative 1, so negative 2 square root of 15. Okay, letter C. Oops. I pops out on top. Square root of 20 is 4 times 5. On the bottom, I pops out. Square root of 2. The i's are going to cancel out, actually. And the square root of 4 is a 2. So now this statement is 2 root 5 over root 2. We don't leave the root in the bottom. So I'm going to multiply by root 2 over root 2. That gets me on top 2 root 10 over 2. These 2's cancel out. So my final answer is the square root of 10. Another way you could have done this is had the I pop out and the I pop out. So then we have square root of 20 and the square root of 2. The i's still cancel out. And then we can divide the 20 by the 2 because they live in the same radical, the same root. So 20 divided by 2 is square root of 10. So just another quicker way to do the problem. Letter D only has one I, so on top, I'm going to pop the I out, and then I'm going to do, we did this on the previous page, 48 is 16 and 3. On the bottom, 27 is 9 and 3. So my root 3's automatically going to cancel off. On top, the square root of 16 is 4, and then an I over the square root of 3. Letter E, the I pops out, and again, we've done the square root of 48 today many times, so 4I root 3. Square root of 24 is the square root of 4 times the square root of 6. So that gets me 4I root 3 over 2 root 6. The 4 divided by the 2 is going to make a 2 on the top, so 2I on top. I can do the 3 and the 6 and reduce it and do square root of 2 on the bottom, because 3 over 6 reduces to 1 over 2. And then I can rationalize root 2 over root 2. And so then I get 2I root 2 over 2. And these 2's cancel out, so my answer is I root 2. On this page, the purple box tells you how to add and subtract complex numbers, and really the simplest way to put it is to put apples with apples and oranges with oranges. If you're adding two complex numbers, you have to add the apple with the apple and the orange with the orange, meaning you add the real with the real and the imaginary with the imaginary. Same thing with subtracting. And honestly, normally in subtracting, I choose to make it add the opposite, so it still remains an addition problem. So let's try. I'm going to rewrite the first one just so you can see what's happening. And then, obviously, I do not need you to show me as much work, so hang on. In the first one, I'm going to do 3 minus 4I minus 2 plus 6I. And then I like to put the other thing. So 3 is going to go with negative 2. That's going to result in a 1. Negative 4 goes with the 6I, which results in a plus 2I. So there's my answer. You don't need the step in between where I put the circles and circle thing, or put like colored dots. Really, you could have gone from the aligned type on the paper to what I wrote as my final answer. I am going to rewrite the second one and get rid of this addition or this subtraction and make it into addition by distributing the negative in. Negative 4 plus 3i minus 6 plus 7i. So here's a real, oops, not what I wanted. I wanted a highlighter, sorry. Here's a real piece, which goes with another real piece, and so you get negative 10. Here's an imaginary piece that goes with another imaginary piece, which gets you a 10i. And there's your final answer. Okay, now we're going to multiply with complex numbers. So we're going to FOIL, just like you learned a long, long time ago, FOIL. And then we will clean it up from there. So if I FOIL the first piece, the 2 goes into both, and you're going to get 6 plus 8i. Okay, then the negative 3 needs to go into both. Negative 3i. So negative 3i times 3 is a minus 9i. Negative 3i times positive 4i is a plus. Nope, sorry, it's a minus. It's going to become a plus. Step ahead, sorry. A minus 12i squared. I squared equals negative 1. So negative 1 times 12 becomes a plus 12. And then my 6 and my 12 will go together to get me an 18. And my 8i minus 9i makes a minus I. It says to make sure you write them in standard form, so make sure you put real, plus, or minus, then your imaginary piece. Letter B says 4 plus 3i squared, so I have to do 4 plus 3i, FOIL with itself, 4 plus 3i. And then when you FOIL, you get 16 plus 12i plus 12i plus 9i squared. I squared is negative 1, so this last piece becomes a minus 9. 16 minus 9 is 7, plus 12 and 12 make 24i. Letter C is something super awesome because they are conjugates. Their sign in the middle is opposite, but their pieces are exactly the same. So when you FOIL conjugates, I showed you a shortcut a while ago, but it's okay if you don't remember. We can do it again. 6 times 6 is 36. 6 times negative 5i is negative 30i. Positive 5i times 6 is a plus 30i. The point of conjugates is exactly this. This middle term is always going to cancel off. And then 5i times negative 5i makes a negative 25i squared. So the middle terms cancel off. And then I squared is a negative 1. So this becomes a plus 25. And then 36 plus 25 is 61. It says write it in standard form, so technically 61 plus 0i. And this box right here exactly tells you what we got up here. When you FOIL two conjugates, it is really a squared plus a b squared, and not just conjugates, complex conjugates. When you FOIL conjugates, it should be a squared minus b squared, but that I at the end makes the term go from being a minus to being a plus. And honestly, it's really not worth memorizing the rules because you can just FOIL it out every time and get the right answer because you have great algebraic rules. Okay. On the next page, we are finally going to do things that I know you did in Algebra 2. Because some of the other stuff you're like, I mean, I remember I, but I don't remember doing this. But I know that you did this with I because you rationalized. Again, I is the square root of negative 1. And so since I is the square root, I cannot leave him in the denominator. So to fix it, you have to multiply the top and the bottom by the conjugate of the denominator. So 5 plus I over 5 plus I. You're not changing anything because you're multiplying the top and bottom by the exact same thing, so you're multiplying really by a 1. So we FOIL this out on top, and on top we're going to get 15 plus 3i plus 10i plus 2i squared. On the bottom you can FOIL it out, or you can know that they're complex conjugates, so you're really going to get 5 squared minus I squared And then it's going to become a plus because that I squared is going to be negative, so I'll take care of that in a second. On top, this 2I squared is really a minus 2. So on top, 15 minus 2 is going to be a 13. Plus 3I plus 10I is 13I. On the bottom, this becomes a plus 1, so I have over 26. I have to break that into two fractions because it says write it in standard form. So 13 over 26 plus 13 over 26I. 13 over 26 is a half, so the answer is 1/2 plus 1/2 I. Letter B, you can multiply by a negative I, like the conjugate, but you don't really need to. You just need to multiply by an I over an I, because I need that I to become an I squared, because I squared is -1 with no root. So on top, when I do this, I get 3I divided by I squared, 3I over -1, which just results me in a 3I. It did say write it in standard form, so -3I divided by -0 minus 3I. Put it in standard form with that real and complex, or real and imaginary piece, making it a complex number. Okay, so now let's solve again. That we've practiced all our I skills, let's go ahead and practice. This is a quadratic. Right there, x squared tells me that we let quadratics equal 0, so let's move everything over. So I get 9x squared minus 6x plus 5 equals 0. 9 times 5 is 45, and I can't think of any two factors of 45 that add and make a -6. So I'm going to do the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So when I do this, I'm going to get x equals +6 plus or minus square root of b squared, so 36 minus 4 times a times c, all divided by 2a. So on top, 4 times 5 is 20. 20 times 9, this thing right here, it's going to be 180. And then 36 minus 180 is -144. So x equals -6 plus or minus square root of -144 all over 18. So it's -6 plus or minus 12, because square root of 144 is 12i all over 18. And all of those numbers reduce by a 3, so I can divide them all by a 3, resulting in, actually, no, but do it this way. Positive. These are +6. I'm sorry, guys. So I get +6 over 18. I'm going to break the fraction up first. Plus or minus 12 over 18i. That way I can break each fraction up instead of having to double reduce. So x equals 6 over 18 is 1/3. Plus or minus 4 and 18, or 12 and 18 both have a 6 in common. So 2/3 I. Your book writes things as solution set. So 1/3 plus or minus 2/3 I. Okay, on the last page, I think we have saved the best for last. It's one of my favorite things to do because it makes you look so smart, but it's super simple. So the powers of I come in patterns. And a cyclical pattern, in fact, a circular pattern, where I to the first is simply just I. I squared equals I times I, which we know from earlier in the video is -1. I cubed is I squared times I. So now I can take what I had for I squared and what I had for I and multiply them together and get -1 times I, which results in a -I. And then finally, I'm going to fit it in. I to the fourth equals I squared times I squared. I squared we know is -1, so I get -1 times -1, which is just 1. And then anything after that just repeats down the pattern because it's a pattern of 4 things. So for example, I to the 5th. I to the 5th is I to the 4th times I to the 1st. And because I to the 4th is 1, this is what causes this pattern, because 1 times anything is the other thing. And because I squared is -1, -1 times anything is the other thing with a different sign in front of it. That's really what causes this pattern over and over again. So then I get 1 times I, which is just I, which is where I was right here. And then I to the 6th is I to the 4th, 1 times I squared. So I have 1 times -1, which is just -1, what I had right here. And thus goes the pattern. So let me show you how to simplify things, i's to really big powers, because it's super simple. So what you're going to do, straight up long division. This is your work. 4 goes into 15 3 times. 3 times 4 is 12. Subtracty foo-foo. Remainder 3. Whatever your remainder is your power. So for example, this is equal to I to the 3rd. Because I would have gone through the pattern 3 times, and so I would have had 1 times 1 times 1 times I to the 3rd. 1 times 1 times 1 is 1 times I to the 3rd. So this equals I to the 3rd, and we know that I to the 3rd is I squared times I, which is -1 times I. So my answer is just -I. Let's try another one similar to this that isn't in your notes. Let's try another one. Just make one up. So let's try one. Let's do I to the 57th power. So we're going to do 57 divided by 4. 4 goes into 5 once. Drop down the 7. 4 goes into 17 4 times. 16. Subtract is 1. Remainder is 1. This is equal to I to the 1st, which is just I. There's your answer. Okay, let's try letter B. There's lots of different ways to do letter B. I don't super love the way your book does it, so I'm going to do it the way that I think that you would think about it. So negative exponents make me drop that thing down to the bottom. So this is the same thing as 1 over I cubed. I can't leave I on the bottom because it is a root thing. So I'm going to multiply by what I'm missing. I need one more I. If I could get that to be I to the 4th, the other thing you can get it to be is I squared. So getting to I squared or I to the 4th is great because I squared is -1 and I to the 4th is 1, and those don't have i's in them. So I'm going to get to I to the 4th because it's the closest by multiplying by an I. Oh, not an I squared. By an I over an I. And then on top, that makes me be an I. And on the bottom, I get I to the 4th. I to the 4th is the same thing as 1. And this is just an I. So now you have all the information that you need to successfully complete 8.1. Hope that helps you out.